Okay, let's get started. So for those of you that are graduating this year, it's a good time to do so. A lot of interesting things going on out there in the industry with AI. We just talked about the history of AI last week. Another major milestone in the field just fell this week. The game of Go, one of the last remaining human games that humans were still better at computers than. We talked about chess, which fell when?
96.
Sorry?
1996.
1996, right? So it took us another 20 years to master, for computers to master Go, but it seems that we're there now. You can go and have a look at the popular media articles on this, and there's links to the Nature paper that was published yesterday that has a little bit of the technical details in how this actually worked. But at the heart of Google's DeepMind's AI that wins at Go, there's a Minimax tree hiding in there somewhere with some deep learning around it. So go have a look if you're interested. Okay. So we're not talking about deep networks quite yet, but we are talking about neural networks this week. Let me go back to the schedule. We're going to finish our lecture today on artificial neural networks. You're working your way through assignments 2 and 3 this week, where you're first implementing your first artificial neural network. Once you have your ANN implemented, you're going to take your hill climber that you developed in assignment 1, apply it to your artificial neural network, and evolve the synaptic weights of that neural network to do something. We don't have our robot yet, so we have disembodied neural networks. So I'm going to go back and talk a little bit about assignments 2 and 3 now before we go back to lecture 4. Okay, so assignment 2, as I mentioned last time, you start by creating your neurons. Then you create your matrix of synaptic weights. Some of these weights are excitatory and inhibitory. Excitatory synaptic weights mean that the source neuron excites the target neuron that's connected by the synapse. An inhibitory connection means the stronger the source neuron fires, the more it inhibits the firing of the target neuron. In addition to being positive or negative, excitatory and inhibitory, we also have the magnitude of the weight. So a weight that's near 0 means that the source neuron has little to no influence on the target neuron, and the more that value deviates from 0, the stronger the influence. Okay, and then the last image we talked about is an illustration of the neuron values. And as I mentioned, one of the challenges in assignment 2 and 3 is keeping your neuron value matrix separated in your mind from the synaptic weight matrix. So let's come back to the neuron value matrix for a moment. This matrix is a 50 by 10 matrix where each row in the matrix stores the values of the neurons, which range between 0 and 1, and the values of our synapses range between -1 and +1. As you can see from the image here, we set the initial values of the 10 neurons to random values, and then we're going to compute the new values of the neurons based on the values of the synaptic weights and the initial values of the neurons. The trickiest thing about assignment 12, and a few of you, assignment 2, and some of you have already emailed me about this, is step 12. This is where all the magic happens, where we actually fill in all of the rows in the neuron values matrix. I'm not going to tell you exactly how to do this. There's a little bit of math here to help you. So I'm just going to explain it in plain language for those of you that are still a little bit confused about this step. We're going to fill in row 2 through 50. So for each of 49 rows, for each of those rows, we're going to fill in the value of each of 10 neurons. For each of those 10 neurons, we have to go through and compute the influence on that single neuron of the values of the previous 10 neurons. So I've tried to say it in a way to give you a hint about how to set up the code for this. For each of 49 rows, for each of those rows, for each of the 10 neurons. For each neuron, you need to go through and compute the influence of the 10 neurons on that neuron. Okay, should be a sufficient hint to get you through step 12. Any questions about assignment 2? No? Okay, so let's go on to assignment 3. So in assignment 3, you're going to be now not playing with random neural networks, but evolving neural networks to do something. You're going to be using your hill climber to do that. And in this case, what you're going to be doing is actually evolving neural networks to do two different things, an easy thing and a hard thing. So let's start with figure A over here. In figure A, we have a representation of our neuron values again, but instead of 50 time steps, we're only going to go through 10 time steps. So we have a 10 by 10 matrix. Now we're going to start not by setting the initial values of the 10 neurons to random values. We're going to set them to 0.5. So intermediate values, they all have the same values. And in this case, I'm updating my neural network based on some random synaptic values. So my synapses, remember the synaptic weight matrix is a 10 by 10 matrix. That's the thing that's now going to evolve. So in assignment 1, you were evolving a vector of 10 numbers, and you were evolving that vector to maximize all the values in that vector. Now in assignment 3, you're going to be evolving a 10 by 10 matrix, which is the synaptic weights, and the fitness of that 10 by 10 matrix is how well it allows a neural network to do something. So we start with a random 10 by 10 matrix of synaptic weights, apply it to our neural network, update the neuron values in the way I just described, and now we're going to apply our fitness function to compute how well did the neural network do what we want it to do. In this case, what we want our neural network to do is at the 10th and final time step, we want neuron 1 to be on, neuron 2 to be off, neuron 3 to be on, off, on, off. So we want the 10 neurons, which all start with the same values, 0.5, 0.5, 0.5, 0.5, to converge on alternating values. Odd neurons are on, odd neurons are off. So you're going to measure how close those 10 values are to the vector 1, 0, 1, 0, 1, 0. So we have a way to measure how close the final values of our 10 neurons are to our target pattern, and that's our fitness. So here's a random neural network where everything ends up being off, and that gets a pretty low fitness value. I evolve my 10 by 10 synaptic weight matrix using my hill climber, and gradually the neural networks get better and better and better at ending with this on-off pattern until at the end, actually after about 200 generations, I now have a 10 by 10 synaptic weight matrix that when I give that to my neural network and compute the neuron values, it ends up producing that desired pattern. So far, so good? Okay. As you can see from the fitness curve on the right-hand side there, this is a pretty easy thing to do. You're now, after you achieve that, you're going to take out this fitness function that's measuring the values of the neurons at the last time step, and we're going to plug in a new fitness function that's going to select for something that's much harder. So we're only really going to change one line of code from this experiment to this experiment. We're going to start again with random neural networks. And the fuzzy pictures here, I think I just changed something in IMShow. Doesn't matter whether you blur the picture or not. The new fitness function is now going to select for a checkerboard pattern. So at time steps 2 through 10, we're going to look at the patterns, and we're going to want neighboring neurons to have as different values as possible. So if this one is on, its neighbor should be off. And if this one is off, its two neighbors should be on. And it should also differ as much as possible at the next time step. So if this neuron is off at time step 2, it should be on at time step 3, off, on, off, on. So the neurons are going to start to oscillate or blink on and off, and they're going to do it in antiphase to the ones that are next to them. You can see that in this case, my hill climber has done a pretty good job, but not perfect. This is a pretty difficult thing to do. So in assignment 3, we're not looking for you to evolve a perfect checkerboard. If you manage to do so, great. Just to demonstrate by this picture, we can clearly see that your neural network is doing exactly what it's supposed to do or close to it. And we can see a clear difference between a random neural network and your evolved neural network in the easy fitness function case and the more difficult fitness function case. So here's my fitness curve that corresponds to this evolutionary run, and you can see it didn't quite reach 1. If I gave it another, how long is this here? 204. If I gave it another 1,000 generations, would it have found the perfect checkerboard? Maybe, right? It's climbing, hard to say. This is one of the tricky things about evolutionary algorithms. We can't prove that given another 1,000 generations or another 10,000 or another million generations that we would find the optimal solution, but we could probably be sure that it's going to continue to improve and get better. Okay, any questions about assignments 2 or 3 before we jump back to lecture? Okay. Okay, so we were talking about neural networks last time, and just to refresh our memories, we started with our Bratenberg vehicles that have 2 sensor neurons, 2 motor neurons, and they're connected. The sensors are connected to the motors with 2 synapses in the simplest case. For our discussions today, we're pulling the brain out of the body and then throwing the body away, and we were gradually making our neural networks a little more sophisticated. We looked at adding additional connections. So the value of the target neuron is now influenced by all of the source neurons that are pointing to it. We talked about inhibitory and excitatory connections. We talked about weighted synapses. We talked about activation functions. So once you sum all of the influences arriving at the target neuron, you can squash it using an activation function so that your neurons all lie between some desired range, which for us is 0 and 1. And today now we're going to continue by thinking a little bit about what exactly artificial neural networks do. For our purposes, we're going to be dropping them into robots eventually and evolving those neural networks in the way I just described to you so that the robots do something of interest. But what really are these neural networks doing under the hood? Well, ultimately, these artificial neural networks are function approximators. With the right number of neurons and the right number of synapses and the right synaptic weights and the right activation function, you can get most neural networks to compute any arbitrary function for you. This is one of the interesting things about them and the discovery back in the 1980s. So let's look at some very, very simple Boolean functions. Let's imagine that we have a neural network that has 2 input neurons that you see here. We're going to assume binary neurons for the moment. 1 output neuron. Whenever the 2 input neurons are 0, we want an output of 1. When it's 0 and 1, we want an output of 0, and so on. So that's the function that we want our neural network to compute. Which Boolean function is this? And, right? So only when when input 1 and input 1, input 2 are 1, we want an output of 1. In all other cases, an output of 0. Okay, so let's use an activation function as follows. Whatever the raw sum is arriving at our output neuron here, we're going to set that output to 1 if the raw sum is above some value between 0 and 1. If that value is the raw sum, which is x here, is less than or equal to that threshold value, we'll set the neuron to 0. Okay, so we've got 3 numbers that we need to apply to our neural network to get it to compute this function. We need a synaptic weight here, we need a synaptic weight here, and we need to plug in a threshold here, a floating point value between 0 and 1, which will determine how big the sum has to be before the output flips to 1 Otherwise, it flips to 0. What are these three numbers? I mentioned at the very beginning of the course, it's exceedingly difficult to create a neural network by hand. It's possible when we have a relatively simple function, but still not that easy.
Well, if the input value was 1 and the weights were 0.5, then only when both of them were activated, we get 1 in the output.
That's good. All right, so let's try synaptic weights of 0.5. So let's plug in this case down here. 1 times 0.5 is 0.5, plus 1 times 0.5 is 0.5. 0.5 plus 0.5 is 1. So what do we need down here for a threshold value to make sure that our raw sum of 1 gives us a 1? Something higher than 0.5, right? Anything between 0.5 and less than 1 should be perfectly acceptable. Okay, so let's plug in 0.5 and 0.5 here and 0.8 here. And we can confirm that this works. So we know that 1 times 0.5 plus 1 times 0.5 gives us 1, which is greater than 0.8. So our output is 1. We're good to go. Let's plug in 0 and 1. 0 times 0.5 is 0, plus 1 times 0.5 is 0.5. 0 plus 0.5 is 0.5, which is less than 0.8. So our output is 0. You can do the other two and confirm that this set of synaptic weights and a threshold will give us a neural network that computes the AND function. Okay, so you've seen it done once. Let's try it again. Same neural network, same structure of the neural network. Now we want it to compute the OR function. What are our synaptic weights and activation function here?
You could make the weights a half again each.
Yep.
And then just put the other value something between 0 and a half, so like a quarter.
Exactly. So let's leave our synaptic weights the same and just lower the threshold, right? We want to make sure that these trip over the threshold when the sum is 0.5. Okay, 0.4. So let's just, for the sake of argument, try one of these. Let's take this one, 1 and 0. So we plug 1 and 0 in here. 1 times 0.5 is 0.5, plus 0 times 0.5 is 0. 0.5 plus 0 is 0.5. 0.5 here is greater than 0.4. So we output the correct value, which is 1. And away we go. Okay, so same neural network with different synaptic weights and a different threshold here computes different functions. Okay? That's in essence what you're doing when you're evolving a neural network, but instead of your hill climber looking at two different neural networks, it's going to comb through thousands or millions or billions, depending on how fast your machine is, until it finds a neural network that computes the right function. And for us, the right function is going to be a robot that receives sensory information from outside, transforms that sensory input into motor outputs. The robot moves, the sensor values change, the way it moves changes, and we iterate, and our robot does something, and we measure how well it does that. Not that differently from how we just check to see whether this neural network performs our Boolean function. So far, so good? Okay. Let's try this one. This is the Xor function. So in this case, we only want the output to be 1 when one or the other input is 1, but not both. What set of synaptic weights and threshold do we need here? We need another set of 3 numbers to compute the Xor function. Any ideas?
Well, if you had one synapse be positive and one be negative for the weight, then and the same number like 0.5,
Yep.
both the inputs are the same, then it's going to be 0.
Okay.
But otherwise, the absolute value would be greater than 0.
Okay, so if we set this and this to be excitatory and inhibitory, but to have the same magnitude, then when one, or if there's just a 1 that shows up here, we're going to get a positive or negative value. If both of them are 0, we get 0 at the output. And if both are 1, we get a 1 at the output.
No, 0.
Or sorry, if both are 1, we get a 0 at the output. What's our threshold going to be down here then?
Well, you'd have to do the absolute value of the output.
We'd have to take the absolute value, right? We'd have to apply another function to make this work somehow. So this was, I apologize, a bit of a trick question. There is no set of 3 numbers, given the way I've set up the problem at the moment, that will solve the XOR problem. Last time I mentioned Marvin Minsky, who passed away Sunday night. Professor Minsky became famous in the 1980s for proving that there were certain things that certain kinds of neural networks could not do. And that was one of the things that contributed to the first AI winter. The first proof that these new things called neural networks were not all powerful. There were certain functions that they couldn't compute. And I just showed you the first and most simplest of these counter examples. Again, if you're interested in the history of AI, it's great to go back and have a look at that issue in the history of AI. Okay, so this neural network can't perform XOR, but as was just mentioned, we might be able to add some additional functionality that allows it to do it. So I'm going to introduce now a new building block of neural networks, which we haven't seen yet, which are hidden neurons. And they're called hidden neurons, and we have 2 of them in this case, because they're hidden from the outside world. The input neurons receive information from the outside world, and the output neurons output some number to the outside world. The hidden neurons are hidden or buffered somehow from the outside world, thus the name. Okay, it turns out that if you now add these 2 hidden neurons, you actually can set synaptic weights for these 6, 1, 2, 3, 4, 5, 6 synaptic weights. And you can come up with thresholds for these 3 neurons. So in the brackets here, we want to come up with a floating point value between 0 and 1. So that now, when we supply this at the input, we get this, or we supply this at the input, we get this, and so on. This one's a little bit trickier, so we've got to come up with 6 synaptic weights and 3 thresholds. The thresholds do not all have to be the same. The synaptic weights do not have to be the same. Turn to your neighbor, and perhaps with pen and paper, see if you can figure out what these 9 numbers should be to compute the XOR function.
I think it's work for all of us. Yeah.
Yeah, but they're not.
Now, if they are out, this one's out, and they'll both equal 1.
Because 0 is always going to be 0. No matter which Oh.
Yeah, but
That's not true because of 0. You could turn one of these to 1 or you put your threshold lower down. Right, it's the same type of function.
Or not.
So you get 1 here, so it makes this 2.
x is less than 2. It fires when x is less than 2.
Yeah.
So it makes sense to just like so it has to be greater than
If we have,
less than 2.
I mean, like this one 0.5 and this one minus 0.2.
Yes.
We have a greater
I mean,
than
this one minus 0.5 and this one 0.5.
For the threshold,
Yeah.
you don't need it.
And then that would make
But
1.0,
there's
that
different
would
ways
make
to
0.0.
solve it. But if you just follow this, there's a way
And
to
if
do
we
it.
make this like 0.2, then this one will turn on only when this one is 1.
Okay, I realize it's not even 9 in the morning and you're manually creating neural networks. I promise you this is the last artificial neural network in this class I will force you to do by hand. We'll let evolution do the dirty work from now on. Does anyone think they came up with a solution? Okay, this is a little bit tricky. Before we try and just come up with the 9 numbers without a strategy, let's think about strategy. How might you go about figuring this out? Look at the truth table for Xor.
So maybe if you made it so one of the hidden neurons told you if one of the inputs was 1, and the other hidden neuron told you if the other input was 1.
You could do that, so we could assign different functions to the 2 hidden neurons. We could ask one of the hidden neurons to light up when one of the inputs is 1, and the other hidden neuron lights up when the other input is 1. So it's a good first start. We want to specialize these hidden neurons. We want them to perform subtasks and then combine their partial solutions to the problem. But those are not the subfunctions we want them to compute.
If we have all of the first 4 connections be 0.5 again,
Yep.
right? When one of the ones on the right, their input 2 is 1, they'll fire to both of the hidden neurons. They'll be both 0.5, and then send down to the output of 1, right? So as long as the x is less than 2, which would be the case if both of them fire, then we get XOR.
Okay, I think you're on the right track. We want all these to be 0.5, but let's focus on what we want these 2 hidden neurons to do. What functions do we want these 2 hidden neurons to compute? When they compute it, how do we combine it? Let's come back to the XOR table again. Look at the other truth tables that we had for OR and AND. It's not a coincidence that I showed you a neural network that computes OR and AND before we tackled XOR.
So you really want it to be or but not and.
Exactly, right? So if you look at the XOR truth table, 3 of the rows are exactly the same as the OR table. The only difference between OR and XOR is the last row. And in the XOR function, the last row, the last case, the output should be 0 rather than 1. So let's make one of our hidden neurons here compute OR. What should the other input? What should the other hidden neuron compute? And, right? So we're going to get this guy to do OR in the way we did before, 0.5, 0.5, and 0.4 for a threshold. This guy is going to compute AND, 0.5, 0.5, and 0.8. So now whenever we present the 2 input values, the 2 hidden neurons are going to compute the OR and the AND function for those 2 inputs. How do we combine those results? This is the trickiest part of the XOR neural network.
If it's greater than 0.4, you don't want it. You only want the OR, not the AND.
Right. Most of the time, in 3 of the 4 cases, you want the OR, But in the last case, you want a 0 rather than a 1. You use an inhibitory connection here. This is our AND function over here. The AND function will only light up when both inputs are 1. When it lights up, it will inhibit the output and draw the output down to 0. Okay. There's different ways you can do this, but the basic idea is to understand that we built this neural network by combining functions that we already know work. Right? So here's our inhibitory connection. Our AND function only lights up when both are 1. And in that case, let's actually look at the last, or let's look at 0, 1. This is a good example. So 0 and 1, if we compute the OR, we get a 1 here. I think I have this actually written out. Here we go. Okay, 0 times 0.5 plus 1 times 0.5 gives us 0.5. We have a threshold of 0.4, so it goes up to 1. So the value here is 1. Here we have a value of 0 because we're computing the AND function on 0 and 1. This is 0, so 0 times minus 1 means it does not inhibit. This thing is not on, so it's not inhibiting the output. So the output is free to present the OR function for us. The interesting case, again, is when both inputs are 1, in this case. So now our OR function gives us a 1, and our AND function over here also gives us a 1. 1 times 1 plus 1 times minus 1 is 0. We have our threshold here, the output is 0. So we just saw two simple neural networks that did not have hidden neurons that were able to compute an AND and an OR function. Now we wanted a third function, and our neural network was not up to the task. So we had to add some additional neurons and synapses, and now it was able to perform that function. One of the open problems in evolutionary robotics is if you want to evolve a robot that runs or jumps or picks up an object or cleans up at a construction site, how complex does that neural network need to be to solve that problem? We just learned this week how complex a neural network you need, coupled with a min-max tree to solve or to beat humans at Go. This is one of the challenges. We know in theory there is a neural network that's big enough to solve any function we can imagine, but how big it is and how to label it, how to actually define the synaptic weights and the threshold functions and so on, much more difficult. Okay. So how does this actually work? If we don't want to do it by hand, how do we automate this process of discovering the synaptic weights for our neural network? As we continue our discussion now, I'm going to sort of forget about threshold values for the moment. Let's just focus on synaptic weights. One of the earliest solutions to automating this process is the backpropagation algorithm. Has anybody heard of backprop or know how it works? There's a fair bit of math behind it. We're not going to do the math today. We're just going to do the intuition. Let's imagine we have a bigger neural network here, 2 inputs and 2 outputs, and I've sketched in part of a truth table. It doesn't really matter what this truth table is. Let's imagine that when the input is this, we want the output to be this. Let's imagine we have a neural network that has these 4 synaptic weights. So we set the inputs to 0 and 1. We compute the outputs here. We flow the values down to the outputs. And the values arriving at the outputs are 1 and 1. But we wanted 1 and 0. So we compute the error. There's 0 error here. The first output neuron is doing what we wanted. There's non-zero error here. The second output neuron is not doing what we want to do. So we're now going to, instead of propagating forward from the input to the output, we're going to propagate backward only from the sources of error. So from the second output neuron, we're going to follow the arrows backwards, and we're going to change the synaptic weights at all the arrows that we visit on the way back from an erroneous output neuron all the way back to the input. And the way in which these numbers are changed, we won't go into it, but if you fiddle them enough, you can now get the output to be correct and reduce the error. Okay, that's backprop. This is a learning algorithm, not an evolutionary algorithm. We have a pretty straightforward way of doing this. Works pretty well for a lot of problems, but there's some other problems in artificial neural networks that it doesn't work so well for. And I'll talk about two right now. One of the problems is, as we just saw, if we have a neural network that's too simple, it can't compute the function we want. If the neural network is too complex, it will overfit the data. This is something that humans are often fall into as well. You've got a math exam, you haven't studied all year, you've got 8 hours to cram the night before, you realize there's no way you're going to learn all of the material for the exam, so you decide instead to memorize the solutions from the exam from last year, right? And assuming the professor gives the same exam, you're okay. If he or she doesn't, you're in trouble, right? So memorize rather than learn. Neural networks tend to fall into the same trap, and they fall into that trap as follows. Let's expand our function here, our truth table, if you like. Let's imagine we have some electronic health records. Each row in this matrix corresponds to a patient. Each column in this row represents whether that patient had a particular symptom or not. And the last column indicates whether that patient actually ended up having a particular disease or not. We would like to train our neural network so that if a new patient comes to the hospital and complains of suffering from symptom 1, 3, and 8, but not 4, 5, 6, and 9, our neural network will say there's a very high likelihood that this patient actually has the disease or not. This is actually something that is used in reality. Let's imagine that we gave our neural network a whole bunch of hidden neurons, and we actually ended up giving our neural network as many hidden neurons as they are patients. So if we have n patients, let's imagine we've given our neural network n hidden neurons. Who knows how many different sets of synaptic weights will actually compute this function correctly? Among that set, there is one that will compute this function correctly, but it will do it by memorizing the symptoms of all the patients. So imagine that hidden neuron 1 specializes to recognize patient 1. So this hidden neuron here will only light up when all of the actual symptoms that patient 1 suffered from exist. And it will say, aha, I recognize patient 1. And if patient 1 was diagnosed with the disease, we'll set this weight to 1. If the patient did not suffer from that disease, we'll set this synapse to 0. Same thing for hidden neuron 2 through hidden neuron n. We train our neural network using backpropagation, like I just showed you. This neural network will correctly get all the right answers to this function in the same way that you would get all the right answers if you were presented with the same math exam as there was the year before. What happens if there's a new patient? Can't recognize the disease unless that patient had exactly the same symptoms as one of our patients here and had the same disease outcome. This is a problem in neural networks called overfitting. If we allow the neural network to be too big, it will cheat by memorizing rather than discovering the underlying pattern that's producing the outcome we're interested in. So a neural network's too small, it cannot learn the function. It's too big, it might overfit the data. So clearly we want to find that sweet spot. What is the neural network that is small enough that it will be able to, that it won't overfit, but large enough that it will be able to capture the underlying pattern of the function we want it to learn? Turns out in practice, there's no good way yet to determine what that size should be. It's a completely open problem. Okay. Let's introduce one last building block of artificial neural networks that we will see several times in this class, which are recurrent connections. So far, all of the synapses that we've looked at are flowing from the top to the bottom, or they're flowing forward from our sensor neurons to our motor neurons. What happens if we add recurrent connections? Neuron I points to J and J points to I. In the neural networks you're creating in assignments 2 and 3, you do have recurrent connections. First of all, how do we update a neural network that has these recurrent connections? Well, let's look at motor 1 for a moment. Let's assume that the input was this, and depending on what the synaptic weights are, the values arriving at the 2 motor neurons are this. At the next time step, we get this input, and we want to compute the value here. Well, we take the influence of this sensor neuron, multiply it by the weight of this synapse, plus the value of this sensor times this synaptic weight, plus the value of this neuron from the time step before, and add it to this raw sum, put it through our activation function, and we have the new value of the motor neuron. Yes?
How is the load order determined?
Sorry?
How is the load order determined? Like,
How is the load order? So most of the time we do synchronous updating, which means we take these 2 values and we store them, we take them out of the motor neurons and put them in a temporary variable. And then when we compute this, we refer not really to the neuron itself, but to this temporary data structure that we have.
okay.
Make sense?
Well, sort of.
So that's called synchronous updating because it doesn't matter whether we do motor 1 and then motor 2, or motor 2 and then motor 1, because we're referring to the previous value of the neurons.
Okay.
Actually, we can see this very clearly in our neuron value table. When we compute the new value of neuron 1, we take the value of neuron 2 times the synapse that connects neuron 2 to neuron 1, but we also have this recurrent connection. Neuron 1 is attached to itself. So when we're computing this sum, in that sum is the old value of neuron 1 times the synapse that connects neuron 1 to itself. We have the old values of all the 10 neurons already stored in the row above in the neuron value table. Make sense? Okay. The reason why we want to add in recurrent connections, obviously, once you think about this, is it gives the neural network memory. It's able to perform its current action based on what it currently sees, or what it currently senses, plus what it did before, which was a function of what it saw previously. So if we go back for a moment to our neural networks that do not have recurrent connections, its current output is only a function of its current input. It doesn't matter what this neural network did at the previous time step. Right? There's no memory if you don't have recurrent connections. Make sense? Okay. Okay, let's go back to backpropagation for a moment. Remember, in backpropagation, we apply values to the input. We look to see what the output is. If the output differs from what we want the output to do, we localize where the error occurred, in which output neuron, and then we propagate backwards by following the arrows backwards and changing the weights as we go so that the erroneous output, the local error, is fixed. There's a problem with backpropagation when we apply it to recurrent connections. What is it?
It goes back to, in this case, the motor that didn't have a problem.
Absolutely, right? So we're going to flow back here to the one that didn't have a problem, and we have to keep following the arrows backwards to the input. So we're now going to follow these back, which means we're going to change this one and this one, which means we might reduce the error here, but we might also magnify the error here. Okay, so basically, if we try and do this with a recurrent connection, there's global change, or quite a bit of change that spreads along the synaptic weights. So a good way to think about this is if we have a neural network that has no recurrent connections, backpropagation works nicely because you're going in with tweezers and making changes to only a few synapses to fix the local error. If we have recurrent connections, you see there's a local error, and you go in with a sledgehammer and make changes to all sorts of synapses. Unlikely to just fix the local error that you're seeing. There are more sophisticated learning algorithms that deal with this problem. We're not going to touch on that in this course. Okay. Let's go back to the difference between learning and evolution. I talked about this at the beginning of the class. Supervised learning, as the name implies, is a form of learning. In supervised learning, we know exactly what each of the outputs should be for every kind of input pattern that could arrive, which is fine. But most problems aren't supervised learning problems. We don't know when the robot senses some particular pattern. We don't know exactly which motor should do what at every time step while the robot is moving. Similarly, in the game of Go, for any given arrangement of the board, we don't know exactly what the computer should do at any time, but we can generally measure, did things get better or worse? So the solution to Go and all of the robotics problems that we're going to see, you can think of these as semi-supervised learning problems. Our robot experiences a whole bunch of sensation, the robot moves, and at the end we generally know how well or how poorly it did. We have a fitness function that computes how well it did in whatever we wanted it to do. Semi-supervised. For a given neural network, we can tell that neural network, you did pretty well, you did better than that neural network, you did worse than that neural network, but we can't tell the neural network what it did wrong. We can't use backpropagation to go in and say, motor 14 did the wrong thing at time step 237. We just don't know. The robot fell over or it moved slower than we would like it to do. So that's why we step back and use evolution. Evolution twiddles with all of these weights, tries the next neural network. Maybe the new robot travels a little faster or a little slower than this one. If the robot traveled slower, we throw away that neural network, start to make new changes to the original neural network. If the neural network did better, we keep it, make slight random changes to the synaptic weights, and on we go. Okay, that concludes our very brief discussion of neural networks. It's a vast topic. I've tried to just touch on the basic aspects of neural networks that we'll need for evolutionary robotics. Any questions before we dive into the next lecture? Okay, let's jump back to the schedule just for a moment. We're working our way through the tools of the trade, so you have a bit of an idea now when you evolve your robots what's going on under the hood. Let's talk about the algorithm we're going to use to try and optimize these sets of synaptic weights using an evolutionary algorithm. Okay, we've already kind of mentioned this, evolutionary algorithms. There's a whole field dedicated to this. There's thousands of different kinds of evolutionary algorithms. The one thing they all share in common is they borrow the basic idea of Darwinian evolution, which is descent with modification. In nature, we have a population of organisms. Those organisms have some genetic variation. Some of that genetic variation causes phenotypic variation. So the phenotype, or the body of the animal, the brain of the body, brain of the animal, the way it moves, its behavior is dictated somewhat by its genotype. The ones that manage to survive and produce offspring do so. Those that don't die off. And if we iterate through this evolutionary algorithm in nature for millions and billions of years, you get us and other species. So if you think about evolution in that way, at a very, very coarse level, it's an algorithm. We do the same thing in evolutionary algorithms. So this is the genetic algorithm here, which we'll talk about in a moment. We have our genotypes, which is some data structure that contains instructions for the phenotype, which is the thing that we're going to evaluate to see how well or how poorly it does. We have a population of these genomes, perhaps. We begin by generating them at random. We evaluate the fitness of each of these. We take these numbers, we build our neural network or our robot, see how well or how poorly it does. We delete the ones that are doing worse than the others in the population. Those that survive, we might introduce a mutation, or we might take pieces from two genomes and combine them together. We would do that because we're simulating what mechanism from nature? Sorry? Sex, right? Sex and mutation. That's going to go into our genetic algorithm eventually. All right. So again, I'm going to spend this lecture touching on different kinds of evolutionary algorithms. One thing they share in common is they all borrow this basic idea of populations of things that are evolving over time through trial and error. As we've already seen in the case of evolutionary robotics, the things that are evolving are our robots. So we have an underlying data structure that describes the body and or the brain of the robot, and we evolve it to do what we want. Just for fun, let's have a look at this example. If we do this right, our artificial evolution will come up with a solution, in this case a neural network, that produces the behavior that we want, which in this case is a very crude approximation of brachiation, primates that swing from tree branch to tree branch. There's something interesting about the solution that our artificial evolutionary algorithm came up with here. How is the neural network enabling this robot to solve this task?
You told us a couple of lessons ago, but is using the battery pack as a pendulum.
Absolutely, right? So this is a complete agent. It has a body, it affects the world, and there's a repercussion of that action because it's a body on which physical forces are acting. Our robot here has a heavy battery pack down here, and evolution has figured out that it makes it much easier for the neural network to get the robot to move its hand forward when it exploits the swing and the momentum of this heavy battery pack. We built this as a physical robot just to test that it actually works. And you can see a bit of this exploitation in the physical robot as well. So at the heart of an evolutionary robotics experiment, we're evolving neural networks. The neural networks are causing a physical machine to do something. And if the neural network causes that physical machine to exploit the forces that are acting on it, rather than to work against them, typically that neural network will get higher fitness than another neural network, and we end up with an evolved solution where the physical machine is exploiting the fact that it has a body, not unlike how organisms in humans use their body and exploit the interaction between the body and the physical world. Okay. Okay, before we jump into a discussion about different kinds of evolutionary algorithms, let's arm ourselves with a central metaphor in both biological evolution and artificial evolution, which is an idea, a very old idea in biology called the fitness landscape. And the fitness landscape is an abstract landscape. It's not literal, but it's a way to think about what your evolutionary algorithm is doing once it starts running. So let's look at what these fitness landscapes do. Imagine we have a very high dimensional space, and every horizontal axis in that space, the x and the y and whatever our other dimensions are, define a surface, and every point in that surface corresponds to one possible solution of all of the solutions. So for evolving neural networks, one point might represent one neural network with a bunch of different synaptic weights. Another point represents another neural network with different synaptic weights, and so on. Every point that we sprinkle throughout the space corresponds to one possible genotype or one possible solution to our problem. Now imagine we have an additional dimension, the height dimension here. So the height of the point represents its fitness. The better that neural network does, the higher that point sits in this space. So I can't draw a greater than three-dimensional fitness landscape. So let's start with 2 dimensions. Imagine we had a genotype that had just one number in it. Right? You were evolving vectors with 10 numbers. Imagine you were evolving a vector with just one number. And if it's a floating point number, then of course every point here corresponds to one floating point value. The height of that gene, that genome that contains just one number, the height is the fitness here. So far, so good. Again, this is just a cartoon picture of this landscape here. If you took your hill climber from assignment 1, you collapsed it to just this one number, and I asked you to draw this fitness landscape, it would not look like this fitness landscape. What would it look like? So if we have 0 here, 0.0001 here, 0.0002 here, and 1.0 way over here to the right, what would this fitness landscape look like? How would the heights of those points vary as we went from 0.0 to 1.0?
Wouldn't it just be like the one we submitted to you? Because over time the genotype is getting improved and improved, so the phenotype is consistently better.
We're not talking about the evolution now. We're just thinking about the fitnesses of all the possible solutions, all the possible genotypes, which are going to range from 0.0 to 1.0. What would be the height?
It's linear.
It would be linear,
Yeah.
right? Exactly. So if this, I'm going to just represent this as g, here's 0.0 down here. The fitness function was basically the sum or the mean of all the values in that vector. If you just have a vector with one element, it's that number, right? So it'd be 0.0 here, and the height of the genotype that corresponds to 1.0 would just be linear. Fitness increases for values that are larger. All right, let's imagine, again, the same fitness function, but now a vector with two numbers. So now we have a three-dimensional fitness landscape. What would the fitness surface look like in this space? We're evolving vectors that now have two floating point numbers, and our fitness function is the mean of those two numbers. What would that surface look like?
It would just be like the same linear but for both of them.
Absolutely, right? It would be a sheet, and that sheet would touch the horizontal plane at the genotype that corresponds to 0, 0, and the top piece of the sheet would be at 1, 1, right? It would be a flat surface where we're going upward. Fitness increases from genomes that have values 0, 0, all the way up to genomes that have a value of 0, 1, right? A flat sheet, and a flat sheet or a flat fitness landscape, not flat, I'm sorry, but smooth, is pretty easy to climb. Not so easy if you have another fitness landscape that looks like this, right? So again, imagine we have genomes that contain just two numbers. We have a different fitness function where this combination of values for gene 1 and gene 2 is very fit. This genome that corresponds to this value of gene 1 and this value of gene 2 has very low fitness. Is it going to be a more difficult fitness landscape? Okay, I've already started to use these terms here. We're going to use these a lot in this course. The genotype is the data structure that contains the numbers that we're going to be evolving. The phenotype is the thing that we're going to measure. It could be a neural network, it could be a robot, it could be something else.
Once we're at one of the relative maxima, how do we know that there's
Others.
Yeah.
You don't, which
Okay.
is again is an open problem in the field, and we'll talk about that in a moment. Okay, so now let's talk about some evolutionary algorithms, starting from the simplest one up to some more sophisticated algorithms. You've already implemented a hill climber. I don't know if you'd really consider this an evolutionary algorithm, because in a hill climber there is no population, right? There's just one individual, and that individual produces one offspring. And if the offspring is better than the parent, we keep it. Otherwise, we throw it away. I've introduced this little cartoon down here, which is the basic flow chart for an evolutionary algorithm. We initialize our population, which in this case is just one individual. We score its fitness. We take the average of all the values in the genotype. We do some selection. So there's nothing to select here for the moment. Variation means take the parent, produce a child, and introduce a little bit of variation by changing one or a few of these numbers, and then going back again, scoring the fitness of the child, now doing selection. Which of these two do we throw away? If we throw away the parent, keep the child, vary the child, repeat, repeat, and repeat for 100 generations, or you run your laptop for 8 hours overnight, and when you wake up and check on it in the morning, you press Control-C and stop it and see what the best solution is you have, or whatever your termination criteria is. Okay, so now to build up an intuition for how our hill climber is working, and now to really understand why a hill climber is called a hill climber, let's think about a hill climber operating in this fitness landscape. Again, I can't draw in more than 3 dimensions, so we're going to just do this in 2 dimensions to keep things simple. Let's imagine you're doing a hill climber on a 1-element vector. We have our parent here, which is kind of fit. It produces a child that's not very fit. Throw the child away. And what will happen if we iterate through this process? Where is our hill climber going to end up in this fitness landscape? The rightmost hill, right? It's going to climb this hill. Then what's it going to do? Stop, right? Not a lot. Once there's a parent sitting on the top of the hill, all of the children are going to be less fit. They're going to be thrown away, and we're in trouble, right? Unbeknownst to us, because we don't know what this landscape looks like. This is why we're using an evolutionary algorithm. This space is basically invisible. We don't know what the height of all the points in this space are, so we're trying to climb it and get to the topmost point in this landscape. So you run your algorithm, you have a parent that produces a million children and they're never better than the parent. Great, we found the best solution that's out there.
We're making random modifications though, aren't we? So
Yes.
could we jump to that other hill?
It's
just
possible.
less likely.
Yes, so it is possible that up here there could be a large enough mutation that would land us on the slope of the bigger hill. And if it's going to survive, it better land on the slope higher than the parent. It turns out that that seems pretty easy when we're looking at a fitness landscape in 1 dimension. Think about now adding a 3rd dimension, then a 4th, then a 5th, and a 6th. That higher hill is now much further away from the top of the local hill than it is in 2 dimensions. We could get into the math, but in the interest of time, I don't think we will. So it's exceedingly unlikely, once you're on a local hill, that you're going to make a big jump and land on another hill higher than the parent. Extremely unlikely. So in most problems, your hill climber gets stuck, but your hill climber didn't get stuck in assignment 1. Why not?
Fitness function.
Your fitness function creates a particular fitness landscape, and that fitness, what does that fitness landscape look like?
Getting to 1.
Getting to 1, right? It's flat.
Okay.
There are no local hills if your fitness function is maximize all the values in the genome. It turns out, if I go back to assignment 3 for a moment, there are a lot of local hills when you're evolving a neural network to produce a checkerboard pattern. This is why after 1,000 generations, this was the best that I could do. There is a set of synaptic weights for the neural network that will produce a perfect checkerboard. There is a mountain out there somewhere, the highest peak. I just haven't found it after 1,000 generations. All right, so hill climbers are very easy to implement, very easy to run, but they're relatively weak. They're easily trapped on what are called local optima. So as you can imagine, the name local optima comes because if we just look at a local part of the space, this is the optimum value in that local space, but if we look at the whole space, globally, there is a higher optimum. How do we know, there was a question about this, how do we know whether we're on a local hill or on the global mountain? No way to know. No one's been able to figure that out yet. Okay, so let's empower our evolutionary algorithm here. How can we make it stronger? Well, the simplest thing we could do is create a parallel hill climber. So instead of creating picking a random point in the space and climbing the hill starting from that point, let's drop a bunch of points. So let's create 10 random vectors. Let's drop 10 points at 10 random places in our fitness landscape here. And each of those 10 points starts to climb their local hills. How's the parallel hill climber going to do compared to the plane hill climber?
Has a much higher chance of finding your maximum.
It has a higher chance. Now, whether it has a much higher chance, this is the devil's in the details, right? So in this cartoon here, on purpose, right, it's higher. We did better. We found some more peaks, but we didn't find the global peak, right? We're still just searching locally around those 10 initial points. You can try this out as we start to evolve more sophisticated neural networks. You can try a parallel hill climber versus the plane hill climber and see if it does any better. Probably do a little bit better, maybe not great. So can we do something better than the parallel hill climber? Let's move on to the genetic algorithm. This is probably the most common evolutionary algorithm that's out there. The genetic algorithm starts by looking very much like the parallel hill climber. We create 10 different random vectors. And from time to time, we produce a copy of one of the parents and introduce mutations, but we now also introduce sex. So from time to time, we grab 2 vectors out of our population of 10. We break each of those 2 into 2 pieces, and we take the left side of one and we weld it onto the right side of the other, and vice versa. Okay. So now I'm going to try and represent what the result of that might be in a fitness landscape. Let's imagine we have parent 1 over here and parent 2 over here. We sexually recombine the genetic material from these 2 parents. Child 2 lands here, child 1 lands here, and it happens to land on the slope of the global optimum. Now, child 1, if it produces offspring of its own, might eventually climb to the top of the hill. Why would the genetic algorithm have a higher likelihood of eventually placing a child on the slope of the global optimum compared to just the parallel hill climber? What is it about sex that empowers search?
The mutations can be more drastic, so you could jump from one peak to another peak easier.
Right, so not the mutations being more drastic, but the recombination event is more drastic, right? Mutation by definition means we grab one number and alter it a little bit. Recombination is, as the name implies, recombining genetic material from 2 parents. So with recombination, we can make a larger jump in the fitness landscape, and a larger jump represents to moving further horizontally in the fitness landscape. It's not just the magnitude, though, that empowers our search, because we could just go back to our parallel hill climber and make the mutation larger. We could say grab 10 numbers and mutate them rather than just grabbing one or a few and mutating them. So it's not just the magnitude of change that makes sex so powerful for search.
It's variation.
Variation in which way?
Because you have so many parents, the parents are so far apart.
Yep.
You have all that room in between.
So there's something about the room in between, right? We have 2 parents that are distant from one another, and the children intuitively are falling somewhere in between, right? So a good way to think about this is when sex is working well, what is it doing? It is combining the best of both parents, right? You're hoping that you're going to cut the genome at the right place, that at least for one of the children here, you're bringing the best of parent 1 and maybe jettisoning some stuff that's not so great about parent 1, and grabbing some of the good stuff from parent 2 into the child and jettisoning the part that's not so good from parent 2. Right? That's the hope of sexual recombination. Bringing together the best of both worlds. So whatever it is that allowed P2 to be doing pretty well on this hill, and whatever it is that's allowing P1 to do pretty well on this hill, if we can bring those 2 things together, we increase the likelihood that we bring the child into a space in the fitness landscape that combines these good building blocks together?
Can we use the fitness function to selectively, I guess, select genes that we want to combine?
That is a good question, right? So here, sexual recombination is random. We're choosing where to cut at random. Nature does not recombine at random. Nature has a lot of tricks to make this process non-random. One of them is recombination hot spots. So recent research in biology has shown that on the genome, there's little markers that indicate where recombination should occur. A student who took this class 2 years ago wrote a research paper on how to use that idea of recombination hotspots, build them into an evolutionary algorithm to make recombination less random, to indicate where to cut the genome so that you're more likely to combine good genetic material from two parents. A good example of, again, looking to see what biologists are discovering about how biological evolution works, stealing that idea and bringing it into a computational framework to make it easier for us to search the space of all possible solutions. Remember our discussion a few minutes back about the neural network that computes the Xor function. Imagine you have two neural networks that are kind of doing a good job at performing the Xor function, but neither of them are doing it perfectly. One has figured out the OR function over here, and the other neural network has figured out the AND function over here. Could be the case that there might be a way to cut these two networks, bring the OR together with the AND into a child, which solves the Xor problem. In practice, not such an easy thing to do, and we'll maybe talk about that a little bit later in the course. Okay, so it's why we might introduce recombination. Let's look at a different kind of evolutionary algorithm. This is called the evolution strategy. The evolution strategy is interesting because it applies this idea of non-randomness, but not to recombination. It applies it to mutation. So in an evolution strategy, for every genome and every gene that is stored in the genome, there is another number that piggybacks along with it. And that number represents the step size or the magnitude of mutation that the gene should have. Let's think about this for a moment. And again, let's think through why you might do this by building up an intuition by looking at the fitness landscape. Let's imagine we have this fitness landscape. We have an individual that's sitting here in the fitness landscape. This individual, let's say again, we just have a genome with a single gene in it. That gene has this value, and it has this fitness. And associated with that gene is a step size of 0.1, which means when this gene undergoes mutation, its new value might be 0.1 greater or 0.1 less than its current value. As you can see in the cartoon here, if we mutate this value with this step size, there's a 50% chance that the new genome will be better than the parent. Let's take exactly the same gene. I'm sorry, I moved the point here, but let's imagine this is the same solution. And it still has a step size of +1 or -1 when it undergoes mutation. If this gene has a step size of 0.1, what is the probability of its child being better? Up here it was 50%. Not much at all, right? +1 or -1, the vast majority of its children are going to be worse than it is, right? There's a very narrow window in here of new values that will make the child better. So a step size of 0.1 is not a great choice for this particular gene. What would be a better value of the step size here?
0.05.
0.05, right? Something much, much smaller. But how are we going to figure out which gene should have which step size given where the entire genome is in the fitness landscape? Seems like a pretty tricky thing to figure out.
Could we bake it in that when you're getting consistently children that are worse than the parent to start narrowing down the step size?
Absolutely, right? So the harder it is to climb your local hill, the smaller the change you should make. Turns out the full answer is a little bit more complicated than that because we're not talking about just one gene, right? We have a whole bunch of genes that each have their own values. So we could evolve these numbers themselves. And do a little bit of this trick about make these numbers smaller the longer it takes to improve. So if you see evolutionary strategies, somewhere in that evolutionary strategy, there are numbers that de-randomize how mutation and maybe crossover occurs. Okay, I think we will stop there. You have a quiz due tonight, and you have assignments 2 and 3 due on Monday night. Good luck. We will talk about assignment 4 Tuesday morning. Thank you.